Good morning, everyone. Today, we are going to talk about something very peculiar, how we managed to develop and to create a platform to develop digital twins in a hybrid cloud plus HPC scenario, right? So, first of all, presentations. I'm Diego Ciangottini from INFN, that is the National Institute for Nuclear Physics in Italy. And here with me on the stage, there is Matteo Bunino, that is from the CERN Open Lab. So you might have heard CERN, INFN, it's on the same kind of track. We are doing physics with particles. And so why we are here talking about digital twins? Well, there are several reasons and several institutes and projects that are working into whatever we are presenting today. I give you here just the links so you can check later if you're interested. What are digital twins then? I love this sentence that summarizes very well what should be a digital twin. So it's a digital representation of a real-world system. And yeah, it's not working like that, but kind of, you know? So you have projecting wildfire, and you want to forecast whatever will happen in case of this disaster, or in this kind of other disaster, you want to understand the impact of flooding on your landscape. And then there are other digital twins that can be very useful. And for instance, one that was just mentioned before, in the nice panel that was mentioned before, it's particle detection. So we have this big camera that are trained and projected to create photos, detailed pictures of what happens between particles. Why not creating a digital twin of these big cameras and facilitate our life? And same for noise. We have to do precise measurement. We can simulate noise or teach a machine to simulate the real-world noise we have in our environments. From all these use cases that share very similar needs, we started investigating the possibility to create an engine for digital twins. So something that will serve multiple communities and make them adopt and use resources that are shared across different providers. So you see, interTwin is the project, European project, where we are working this out. And on one end, we have the providers, so that can span from cloud providers to supercomputers, Euro-HPC supercomputers. And on the other side, you have frameworks that users use to do their digital twins. What are the challenges there? So you have to provide a platform that is capable to support all different use cases, all different frameworks. But also, you have to merge that with the offloading capability of heavy tasks on different kind of backends that not necessarily are able to run cloud payloads. Finally, since you have this multiplicity of backends, you want to maintain all your software as interoperable as possible. So you want to reproduce the very same results on any kind of backends. So the challenge, in a nutshell, we have a distributed heterogeneous resources. Good. And then we need to put on top a common interface. Two problems come from here. So how we give access to the users to this platform, and how we maintain all our workflows consistent to each other. So, for instance, starting from the software and the container zoology that can come from different container runtime interface. Plus, we know that we have lots of users that actually don't care where they are going to run. They just want their jobs to be done. Fortunately enough, in this case, but also in particle physics, we start to converging to a set of tools that are cloud native. So the main interface that we face, in most cases, is Kubernetes. So we left out just with a question, how we can merge a Kubernetes API access to different kind of resources. And we listened before for quantum computing is kind of the same challenge. So someone told me that on Tuesday there was a nice talk about this technology that is interlinked, totally not presented by me. So there is a demo for the solution that I'm going to briefly introduce here. So if you're curious, just check it out. And the idea is to create a pluggable system where we put adapters on top of the remote resources that we want to control through the Kubernetes cluster. And we try very hard to keep the requirements for the providers the less invasive possible. So you plug interlink on top of your edge node here, and you're good to go, basically. You create a virtual node based on virtual kubelet technology that is capable to schedule pod on your SLURM supercomputer, for instance. And yeah, so why we choose this way? Well, in this way, we are capable to grant our users access to Kubernetes in interface with no compromise. With no CRDs, everything just runs like playing Kubernetes. So you have pods with annotation, you select a virtual node, and voila, you go end up into supercomputers that do your machine learning pipeline or your digital twin, and everything is reported back once done. It's a community effort, of course, and the community is very interested in understanding how they can plug their own providers. And in fact, we have not only scientific use case, but you can find here in the list also enterprise that try to plug their container as a service solution in this way. And the latest news is that now this project is part of the Cloud Native Sandbox. We just passed the vote a couple of months ago. And so I take this occasion to say that it's a really thin and simple interface that is perfect for introduction of new commitment or other communities. So we are really looking into get more people on board on this. So we have an interspace, if you wish. So a set of frameworks that can run on different Kubernetes clusters that, thanks to this adapter, can run on VMs with GPUs, on HTC system like HD Condo. On Quantum, we are trying to see how what we can do with this with a Galicia supercomputer, quantum computing. And then we have HPC centers that were where we started. We need these kind of centers to create digital twins. So we create a kubearray, for instance, from plain Kubernetes Helm chart. This spawn up different worker nodes, but pay attention, these worker nodes are living inside a supercomputer. Everything's seamless and completely, the users are completely unaware of everything is happening below. Cool. Now we have big powers, we have also big responsibilities, because we need to provide a consistent environment for our users. We need, in other words, a spaceship. And a spaceship needs to provide us with a consistency of workflows. We need to check our workflows. We need reproducible results. And yes, we can do with the CI system that we have nowadays, but not without locking ourselves into a custom solution or reusing and copy-pasting nightmare that you might know very well. What Dagger provides? The solution we choose for this is a runtime, basically, that it's meant to create composable software. And gosh, scientists love composable things. So we took a look at that, and yeah, we got pretty far, because we have now repeatability of our results. We can compose all our software in an efficient way, and we can also observe what happens when we build and we test stuff. So this is all good, but even more, we have a universal type system, so we can code our pipeline in a very efficient way. We have an open platform where we have caching for our artifacts, and we have built-in observability. And finally, yeah, the new thing is that we also have native integration with LLM. That might be of use in the next years. This is the situation. Different modules that does different things. all together can be composed to create different pipelines that we can run on our machine, first of all. So on your laptop, you can run those pipelines. But the very same pipeline we run, we run in the Dagger engine in your CI system. All right, so just one last news. This sandbox that you send around between your local machine and your remote machine can also host LLM agents. So we can have some improvements of our workflows based on our set of pieces that we put into the puzzle. And we ship also all our software in a resilient and efficient way. For more details, I leave all the links during the presentation. So now we have an interspace and a Daggerverse that can match, provide us the capability to run on external resources through a Kubernetes cluster. But those Kubernetes clusters can run also in a sandbox on our CI pipeline, granting us all the capability to be double-checked before we push changes to production. And we're using also other modules that we use in other use cases. So pretty good so far. I would say we are pretty satisfied. And we are all set for the launch now. Please, Matteo, introduce to what we did with all this stuff.
Thanks a lot, Diego, for the introduction. Very nice. Yeah, so let's see in practice what we have been doing with InnerLink and Dagger. So first of all, as introduction, I'm from CERN Open Lab, which is this entity in the CERN IT department, which is responsible for establishing collaborations with industry and academia. So here you can see our partners. And I mean, of course, feel free to reach out if you have ideas, would like to collaborate. We're always open to new collaborations. And as Diego was saying, we are interested in digital twins, for instance. So we're participating into the interTwin project. And in this project, we are responsible for developing a component for scalable AI workflows for scientific digital twin applications. This component is implemented as a Python library, which is called iTwin.ai. And you can imagine that as a toolkit that provides scientists with different functionalities to support distributed machine learning, training, distributed hyperparameter optimization, can support PyTorch and TensorFlow, and also has a strong focus on the machine learning tracking, so tracking the machine learning metadata that is generated during training. For instance, also allowing you to store the models, to connect to a models registry where you can store the models and version them and so on and so forth. And for this, we're using, for instance, MLflow. When I talk about distributed machine learning training, I'm actually thinking of two different models. One is the pure data parallel distributed training, in which we have a model which is replicated on different GPUs, on different nodes, potentially multiple nodes, and the dataset is partitioned. So each local replica of the model will actually access a subset, a specific partition of the dataset. On the other hand, we can also support model parallel and hybrid model parallel and data parallel training, so which is the image on the right. In this case, the model is too large to fit on a single GPU, which is pretty common nowadays for very large language models or like transformer-based models. So in this case, the model is distributed over multiple GPUs. And to do this, we rely on popular frameworks such as PyTorch, Horvath, Ray, and DeepSpeed. Another key feature, as I was saying, is hyperparameter optimization. So in this case, you can imagine you have a tuning configuration in which you define the ranges for your hyperparameters, and then the iTwin.ai trainer will make sure that individual training trials are run in parallel, so distributed over HPC infrastructure, over multiple nodes, and in an optimized way. And to do this, we rely on RayTune. So let's see some examples of digital twin use cases that we have in interTwin that have been currently integrated in iTwin.ai. These are not the only ones, but let's see two of them. So the first one, it's tackling, it's focusing on the domain of environmental sciences, so on hydrological modeling and developing AI model to improve early warnings for droughts. The other is from physics. We're collaborating with people working on the data collected at the Virgo interferometer, which is meant to measure gravitational wave signals. And what they would like to do is to use AI-based model to denoise the signals captured by the detector. So here we can see an example of, let's say, scalability analysis that we did with iTwin AI. So on the left, we can see a plot in which we compare different distributed frameworks, how they scale for the same model on the same dataset, of course. And on the right, we can see an example of energy benchmarking. So we're also interested in studying how different distributed frameworks for a specific model, for a specific use case, and a specific dataset, how much is the energy consumption, and in other words, to highlight the different trade-offs. Another example, as I was saying, in this case, we used iTwin AI to perform hyperparameter optimization of a model for hydrological modeling. And with iTwin AI, we were able to reduce the validation loss of almost 75%. So how do we make sure that the code that we're developing in iTwin AI is always consistent? So as I was saying, iTwin AI is this abstraction layer on top of popular distributed machine learning frameworks. So the users will provide a training configuration and a tuning configuration, and then the trainer will abstract out from the complexity below, which are basically different distributed machine learning frameworks, and also from the HPC infrastructure. Of course, we can write some tests, and we do that. And we have, of course, some unit and integration tests that we use, for instance, to test the abstraction layer that we developed for the loggers, or for some utility functions, or some general purpose unit and integration testing for whatever, any kind of feature. These are classical, let's say, these are traditional unit and integration tests and can be run anywhere. And these are not the topic of this talk. You already know them. The problem is that some features of iTwin AI are inherently distributed. So how can we test these features, everywhere? Like how can we test these features without having access to GPUs, to multiple nodes? An example is the worker rank assignation. So what does it mean? When we have, for instance, data parallel training, each process assigned to a specific GPU is also assigned different ranks. And the ranks are needed in the collective communication, in the communication between the workers. So how can we test this on a laptop? Of course we cannot. I mean, we need specific infrastructure. Same is for the collective operations, such as all gather, barrier, and so on and so forth. So how can we make sure that our software is actually implementing these operations in the right way? Other examples are, for instance, saving and loading checkpoints in a distributed machine learning setting, end-to-end integration testing for distributed machine learning training, and also the possibility, also testing that we can run distributed machine learning training under hyperparameter optimization. So there is like a hierarchy. So we have a high-level distribution, which is the hyperparameter optimization, and then each trial is also distributed. So how can we test this? Well, that's the topic of the talk, of course, and we're also interested in repeating these tests for all the frameworks that we're actually using. So you can see that there's a kind of matrix that is building up here. Oops. Yeah. So how do we actually run the tests in practice? So we have distributed launchers which are compatible with the distributed machine learning frameworks. For instance, for PyTorch, so for Torch DDP, there's TorchRun, if you know it, if you ever heard of it. And this will allow to spawn multiple processes, and each process is basically just a PyTest command. So I guess you're familiar with PyTest. And then each test case will actually communicate with the other test cases using a collective communication backend, which is provided by the distributed machine learning framework. And the whole thing will then be possible to be tested on HPC. So this is a high-level representation of our tests. Now, let's put everything together. We saw digital twins, HPC, AI, hydrological modeling, gravitational waves. So great, but then how do we actually automate our tests on HPC in practice? We have our code on GitHub. On GitHub, we also keep our CI workflows, such as software quality assessment, unit tests. We build the Docker containers on HPC. Great. But how do we integrate, then, the HPC resources into GitHub? So first ingredient is Dagger pipelines. So Diego already made a very nice introduction. The great benefit, in my opinion, what I noticed at least, is that you can avoid to push and pray. Okay, you have a reproducible CI that you can run on your laptop, you can run it on GitHub, on GitLab, wherever you want. It will always be the same, and it's based on containers, which is pretty useful for us. And second, Dagger pipelines allow to spawn on-the-fly services in the pipeline, and this will be pretty useful for the next step, which is putting everything together with interlink. So on the left, we have the cloud side, so GitHub, code, CI pipeline, Dagger pipeline, basically. And on the right, we have the HPC, so the remote HPC supercomputer. They use different technologies. So on cloud, we can, so on GitHub, we can build Docker containers. But then when we want to run on HPC, we actually need Singularity containers. So part of the CI, let's say, pipeline also consists in converting the Docker containers into Singularity containers before they're actually tested on HPC. So it's, but let's see more details what the pipeline looks like. So first of all, of course, we build a Docker container and we run some unit tests, like simple CPU-only tests that can be run on GitHub. Next, we convert the Docker image to a Singularity image file, and we push it to some, let's say, Singularity registry. It's not shown here, but and then we actually deploy interlink onto, well, actually we deploy K3s inside the Dagger pipeline on the fly, and on top of K3s we deploy interlink. So now, by magic, we're able to use interlink and submit jobs to HPC within this pipeline. And so the last step, let's say the central step in this picture, is let's actually run the tests on HPC. So we use interlink, we submit the jobs. If the tests are passing, great. We can publish the new version of the container image both to a Singularity image registry and to a Docker container registry. So this is actually implemented as a Dagger module, so you have also a link. Yeah, you can find it on the Daggerverse. I'm sure everyone can read here, but this is, of course, just to give an overview of the code. So in practice, how does it look like? We've been defining 3 Dagger types are called. So first one, INFN AI. So that's where we have the logic to build a container, to connect to interlink, to run the tests on HPC. I mean, to convert to Singularity, everything, all of this is on GitHub, so of course you can always have a look at that. Then we have the interlink, type, which allows to bootstrap the interlink service. And the last one is the Singularity step, which actually, the Singularity type, which actually allows to convert the Docker container to a Singularity image. So here we have some examples on how to use this pipeline. So on the left, if you can see, you can actually see some examples of how a container, how a CI/CD CI pipeline can be built in a modular way. So if we want, we can just build a container and publish it, or build a container and open a terminal in it immediately, or build a container, test it on CPU only, let's say environment, and publish if you want. So it's really modular. Whereas on the right, we have some examples on how to actually spawn interlink and submit jobs from the same Dagger pipeline. So you could even just use interlink without caring about all the rest. On the right, you have some examples on how to do that. So let's see an example. So this is the end-to-end workflow. So we launch, we push, let's say, to GitHub. This will trigger some, let's say, GitHub actions, so some workflows, which under the hood will run a Dagger pipeline. Here you can see the trace of the Dagger pipeline on the Dagger cloud. So, of course, I cannot open the tabs, but it's very nice because you can navigate inside the whole tray. So here we can see that at the beginning we were passing some variables as secrets. Then the container was built, and the last step is actually the release pipeline. So deploy inner link, run the test on HPC, and push the final images. And here we get the final images. So the Docker images will be pushed to the GitHub containers registry, whereas the Singularity images will be pushed to a Harbor registry, which is currently hosted on CERN resources. And here you have the complete user story. Now let's wrap up. What can we currently do? Well, of course, build containers in a reproducible CI pipeline thanks to Dagger. We can integrate de facto HPC into GitHub, and we can automate the whole thing. So integrate the CI tests on HPC through GitHub using GitHub Actions, Dagger, and interlink. Next steps are to scale up, so we can create more tests. For instance, as I was sharing before, we are really interested in studying the scalability of our code. So we're not only interested in checking that the code is running, but we also want to make sure that our trainer, when we make changes to our trainer, we're not actually introducing some inefficiencies. So one set of tests could be having some baseline code, some baseline reference, actually making sure that the code is actually scaling, is always scaling the same way or even better. Or on the other hand, also studying the energy consumption for similar reasons. Second could be integrating new HPC centers. So at the moment, we've just been working with Vega in Slovenia. And the third one, it's pretty interesting because we could, so the whole CI that we've been writing so far is for our code, so for iTwin AI, for the abstraction layer. But we could extend this to any use case that would like to write dry runs tests for their, let's say, machine learning training, for instance, before committing to very large jobs on HPC, which take time and maybe you need to wait a lot in the queue. And it's not very uncommon to allocate resources on HPC for many hours on many GPUs, and then for some mistake, it just crashes, right? So, but sometimes the allocation is not always released immediately. So you may be paying, you may be charged, let's say, for compute time anyway. So it could potentially be pretty useful for our users also to extend what we've been developing to their let's say, day-to-day development for HPC code, for AI on HPC. And with this, thanks a lot for attending. You can, of course, leave a feedback. And I left some references if you want to know more from the slides. But yeah, thanks a lot.
Yep, thank you. And if you are interested in any of this, of course, we are here until the end of the day, so you can reach out and we can talk about that.